The moment a city fails, it does not announce itself with clarity. There is no single siren, no universal signal that tells millions of people to move at once. Instead, collapse begins as friction. Traffic lights stop coordinating, cellular networks degrade under sudden spikes, elevators stall between floors. Within minutes, dense urban systems built for efficiency, not resilience, begin to clog. And when movement stops in a city designed around constant flow, danger multiplies faster than most people can process. The real threat is not the initial disruption, it is the convergence of millions of individuals all attempting to escape through the same visible pathways at the same time. To understand why this becomes deadly, you have to look at how cities are engineered. Urban layouts prioritize economic throughput. Major arterial roads, public transit corridors, and centralized hubs. The systems are optimized for predictable daily cycles. Morning inflow, evening outflow. What they are not designed for is simultaneous, full-scale evacuation. When that happens, the entire transportation grid enters a state known in traffic engineering as gridlock cascade, where one stalled segment propagates failure backward across the network. A single blocked intersection can immobilize kilometers of roadway within minutes. Most people assume escape is a matter of speed. Get into a car, choose the fastest route, and leave early. That assumption is not just flawed, it is dangerous. In real emergency scenarios, speed is not determined by your vehicle or your urgency. It is determined by system capacity, and system capacity collapses under synchronized demand. The misunderstanding comes from everyday experience. Under normal conditions, alternative routes exist. GPS navigation systems dynamically reroute traffic, but during mass emergencies, these systems amplify congestion instead of solving it. Algorithms push thousands of users toward the same optimal path, unintentionally creating choke points where none existed minutes before. Hidden beneath this visible network is a second layer of urban infrastructure that most people never consider. Cities are not just streets and highways, they are layered systems, utility corridors, maintenance access routes, service alleys, flood control channels, rail maintenance paths, and pedestrian networks that were never designed for public evacuation but can function as critical alternatives when primary systems fail. These routes exist because cities must maintain themselves without interrupting surface activity. Engineers design redundancy for maintenance, not evacuation, but under the right conditions, these redundancies become escape pathways. Evidence of this can be found in multiple real-world incidents. During large-scale evacuations caused by natural disasters, official reports consistently show that primary evacuation routes reach capacity far earlier than predicted. In contrast, secondary and tertiary pathways, often unmarked or underutilized, remain partially functional for longer periods. Studies in emergency management have documented that individuals who deviate from main corridors and use decentralized movement patterns have a higher probability of avoiding complete immobilization. This is not because those routes are faster in normal conditions, but because they are less visible, less intuitive, and therefore less crowded during crisis conditions. The survival implication is clear and uncomfortable. The routes most people trust are the first to fail. Visibility becomes a liability. Wide roads, highway on-ramps, and major intersections attract mass movement, and mass movement creates pressure. Pressure leads to conflict, delays, and eventually total stagnation. Meanwhile, narrower, less obvious pathways, service roads, back alleys, pedestrian cut-throughs remain viable longer precisely because they are ignored. But this introduces a second layer of risk. Hidden routes are not inherently safe. Many are poorly lit, structurally neglected, or designed for limited use. Flood channels can become deadly during heavy rainfall. Underground passages may lack ventilation or emergency exits. Rail corridors carry the risk of active lines or electrified systems. The misunderstanding here is assuming that less crowded equals safe. In reality, these routes require different kind of awareness, one based on understanding infrastructure design rather than relying on crowd behavior. The science behind this comes from network theory and load distribution. In any interconnected system, nodes with the highest visibility and capacity attract the most load. Once those nodes exceed their threshold, failure spreads outward. Lesser known nodes, even if smaller, maintain functionality longer because they never reach the same load levels. This principle applies to power grids, data networks, and urban transportation systems alike. The key is not finding the biggest route, it is finding the route that remains below its failure threshold when everything else exceeds it. Historical data reinforces this pattern. After major blackouts, for example, vehicle movement often halts, not because roads are physically blocked, but because intersections lose signal coordination. Drivers default to aggressive or uncertain behavior, creating micro conflicts that scale into macro level congestion. In contrast, areas with simpler, less signal dependent layouts, such as grid back streets or mixed use service lanes, retain limited but functional flow. These areas were not designed as evacuation routes, but they inadvertently become them when primary systems fail. This leads to an escalation that most people are unprepared for. As primary routes become immobilized, people abandon vehicles. What begins as a traffic problem becomes a human density problem. Thousands of individuals transition from vehicles to foot movement simultaneously, often within confined spaces. Sidewalks overflow. Intersections become chaotic. At this point, the dynamics shift from traffic engineering to crowd dynamics, where factors like panic, visibility, and perceived direction of safety dictate movement more than logic or planning. And here is where hidden urban escape routes become critical, not as shortcuts, but as pressure relief valves. Small pathways that connect between major blocks, maintenance corridors that bypass intersections, even drainage routes that cut across urban zones. These can allow movement to continue when everything else stops. But accessing them requires prior awareness. In a crisis, there's no time to discover these routes for the first time. Cognitive overload, stress, and environmental noise reduce decision-making capacity. People default to what they already know. The transition from understanding to application is where most fail. Knowledge of infrastructure must exist before the event. This does not mean memorizing every alley or service tunnel. It means recognizing patterns, where utilities run, how cities are layered, where maintenance access points are likely to exist. It means understanding that the most obvious path is often the most fragile under stress. As systems continue to degrade, the window for effective escape narrows. What begins as inconvenience becomes entrapment. Elevators stop working, forcing vertical evacuation on foot. Water pressure may drop, affecting sanitation and fire suppression. Communication breakdowns lead to misinformation, causing people to move in the wrong direction or remain in place when movement is still possible. Each of these factors compounds the others, creating a feedback loop that accelerates collapse at the human level, even if the physical infrastructure remains partially intact. And this is where the next layer of risk emerges, one that most people never consider until it is too late. The difference between structural accessibility and functional accessibility. A route may exist on a map, but that does not mean it is usable under emergency conditions. Locked gates, security barriers, debris accumulation, and environmental hazards can render theoretically viable paths useless. The hidden science here lies in understanding not just where routes are, but how they behave under stress conditions. Because when the city stops flowing, survival is no longer about distance. It becomes about navigating failure itself.